At first glance, it looks like chaos in the sky. Rockets streak across the darkness, leaving glowing trails as they race toward the city below. For the people on the ground, there is almost no time to react. Within seconds, those projectiles can travel miles, turning distant launch sites into immediate threats. But modern warfare has changed the equation. Before the rockets even reach the edge of the city, a network of radar systems begins tracking every object in the sky. Computers instantly calculate speed, trajectory, and likely impact points. And then something remarkable happens. Another missile launches, not to attack, but to intercept. In a matter of seconds, a defensive missile races upward, guided by radar and advanced targeting systems. If everything works perfectly, the interceptor reaches the incoming rocket before it can reach the ground. The explosion you see in the sky is not random. It is the result of one of the most complex and technologically advanced defensive systems ever created in modern warfare. Modern missile attacks rarely come one at a time. In many conflicts today, rockets are launched in waves. Sometimes dozens of projectiles are fired within seconds. The objective is not always precision. Instead, attackers often rely on sheer numbers. By launching many rockets at once, they attempt to overwhelm defensive systems and force difficult decisions. Every air defense network faces the same challenge. It cannot intercept everything. Interceptors are expensive, and launchers carry a limited number of missiles. That means every interception decision matters. When radar systems detect incoming rockets, computers immediately calculate where each projectile is likely to land. Some rockets are predicted to fall in open areas or empty fields. Those may be ignored. But rockets predicted to strike populated areas, infrastructure, or military bases are treated very differently. For those threats, the defense system launches interceptors, and once the interceptors leave the launcher, a race begins in the sky. When a rocket barrage begins, the first challenge for defenders is detection. Radar systems constantly scan the sky for objects moving at extremely high speeds. The moment a rocket is launched, the radar begins tracking it. But detection is only the first step. Within seconds, powerful computers calculate the rocket's path. They determine how fast it is traveling, how high it will climb, and most importantly, where it will land. If the projected impact point is outside the city, the system may decide not to intercept it. This might seem surprising at first, but interceptors are limited, and using them efficiently is critical. However, if the rocket is predicted to strike a populated area, the system reacts immediately. An interceptor missile launches from the defense battery. Guided by radar and advanced targeting algorithms, it climbs rapidly toward the incoming threat. High above the battlefield, two missiles are now racing toward each other. In large-scale rocket attacks, the goal is rarely precision. Instead, the objective is volume. Attackers launch as many rockets as possible within a short window of time, creating what military analysts call a saturation attack. The idea is simple. Even advanced defense systems can struggle when dozens of projectiles arrive at once. Every incoming rocket must be detected, tracked, and evaluated. Computers must calculate where it will land and whether it poses a real threat. At the same time, interceptor missiles must be launched quickly enough to meet those rockets in midair. The challenge is timing. If interceptors launch too late, the rocket may already be descending toward the city. If they launch too early, the targeting calculations may be wrong. So within seconds, radar systems, computers, and interceptor batteries work together in a coordinated defense network. In the sky above the battlefield, dozens of missiles are now racing toward each other. When an interceptor missile launches, it immediately begins climbing toward the incoming rocket. But unlike traditional missiles, interceptors are not simply aimed at a fixed target. They rely on continuous radar guidance. Ground radar systems track both the incoming rocket and the interceptor missile at the same time. Computers constantly update the interceptor's flight path, adjusting its trajectory as the two objects approach each other. In many cases, the interceptor does not actually strike the rocket directly. Instead, it detonates nearby. The explosion creates a cloud of high-speed fragments designed to destroy or disable the incoming projectile before it reaches the ground. From the perspective of someone watching from the city below, these explosions appear as sudden flashes in the night sky. Each flash represents a successful interception. But even as one rocket is destroyed, others may already be approaching. In theory, missile defense systems are designed to intercept incoming threats. In reality, the situation is far more complex. During large rocket attacks, defenders must deal with multiple variables at the same time. Some rockets may travel faster than others. Some may follow slightly different trajectories. Weather conditions, radar visibility, and communication delays can all influence the interception process. And then there is the problem of numbers. If dozens of rockets are launched simultaneously, defenders may have to choose which ones to intercept first. This creates a constant balance between efficiency and urgency. Air defense systems are not simply reacting to rockets, they are managing a limited set of resources. Every interceptor missile represents both protection and cost. And every interception decision shapes how the defense system responds to the next wave of incoming threats. Saturation attacks reveal one of the biggest challenges in modern missile defense. Interceptor missiles are extremely sophisticated weapons, but they are also expensive and limited in number. Every time a defense battery launches an interceptor, it uses one of the missiles stored in its launcher system. Reloading takes time, and during a heavy barrage, that time can become critical. This means defenders must constantly manage their inventory of interceptors. Launching too many too quickly could leave the system vulnerable to later waves of attack. Launching too few could allow dangerous rockets to slip through. This is why modern air defense systems rely heavily on predictive targeting. By calculating where rockets are likely to land, the system focuses its resources only on the most dangerous threats. The result is a defensive strategy that combines technology, timing, and careful decision-making. Eventually, every rocket barrage reaches its final moments. Some rockets are intercepted high above the battlefield. Others may fall harmlessly in open areas where they pose little threat. By the end of the sequence, the radar screen begins to clear. But what remains is a clear lesson about modern warfare. Missile attacks are no longer simply about launching weapons. They are about overwhelming systems, forcing difficult decisions and testing the limits of defensive technology. At the same time, missile defense systems are constantly evolving. Each interception teaches engineers and military planners more about how these battles unfold in real time. The sky above the battlefield becomes a laboratory of modern warfare, where every interception, every explosion, and every radar signal contributes to the next generation of defensive strategy. At this stage of the engagement, the battle has moved entirely into the sky. Rockets and interceptors are now crossing the same airspace, moving at incredible speeds. For the defense system, the objective is no longer just detection, it is coordination. Multiple radar stations track each projectile, while command systems calculate interception points in real time. Every interceptor missile must be launched with precise timing. If launched too early, it may miss the target completely. If launched too late, the incoming rocket could already be descending toward the city. This is why modern air defense networks operate as integrated systems. Radar, command software, and interceptor batteries work together as a single defensive shield. The explosions seen high above the skyline are not random events. Each one represents a carefully calculated interception. And each successful interception reduces the number of rockets that could reach the ground. As the engagement continues, the radar picture begins to change. Earlier, dozens of incoming rockets were moving toward the city. Now, many of those tracks have disappeared. Each disappearance represents an interception. But even successful interceptions do not end the challenge. Defense crews must remain alert for additional launches. In modern conflicts, rocket attacks often come in waves. The first wave may test the defensive system. Later waves attempt to exploit weaknesses. This is why air defense systems remain active even after the initial barrage appears to end. Radar stations continue scanning the sky. Interceptor batteries remain ready. Because in modern warfare, the battle between offense and defense is rarely decided by a single exchange. Instead, it is a continuous cycle of attack, detection, interception, and adaptation. What makes modern air defense systems effective is not just the interceptor missiles themselves. It is the structure of the entire defense network. Most systems operate using layered defense. Radar stations detect threats from long distances. Command centers analyze the incoming projectiles and determine which defense batteries should respond. Interceptor missiles are then launched from positions that provide the best possible interception angle. By placing these systems across multiple defensive rings, cities gain several opportunities to stop incoming threats before they reach the ground. But even with advanced technology, missile defense remains a constant challenge. Every new offensive tactic forces defenders to adapt their strategy. And every interception provides valuable information about how the system performs under real combat conditions. When the night ends, the sky above the battlefield grows quiet again. But what happened in those few minutes reveals something important about modern warfare. Today, battles are no longer fought only on the ground. They are fought in the sky, between missiles traveling at incredible speeds. Each interception represents a complex chain of technology, coordination, and decision-making. Radar operators, command systems, and interceptor crews all work together to create a defensive shield. And while no defense system is perfect, these networks have changed the balance between offense and protection. Missile defense does not eliminate the threat entirely, but it can dramatically reduce the damage caused by large-scale attacks. In the future, new technologies such as laser interception and AI targeting may push these systems even further, and the race between offensive weapons and defensive technology will continue to shape the battlefield of tomorrow. After the final interceptions, the radar picture becomes much clearer. Moments earlier, the screens were filled with dozens of incoming missile tracks. Now most of those signals have disappeared. What remains is a record of how the defense network responded. Each interception reveals how radar detection, command coordination, and interceptor guidance work together in real time. In many ways, these engagements function as live tests of the entire defensive system. Engineers and military analysts study the data collected during every interception. They examine radar accuracy, interceptor response times, and the effectiveness of targeting algorithms. This information becomes critical for improving future defense capabilities. Modern warfare evolves quickly. Attackers constantly search for new ways to bypass defensive systems. Defenders respond by improving detection networks, interceptor technology, and command coordination. This ongoing cycle of adaptation shapes the future of missile defense. And every engagement contributes new lessons about how these systems perform under real battlefield conditions. Missile defense systems represent one of the most complex technological challenges in modern warfare. They combine radar detection, command coordination, advanced computing, and high-speed interceptor missiles. All of these systems must work together in perfect synchronization. But even the most advanced defenses cannot guarantee total protection. Attackers may attempt to overwhelm defenses through saturation attacks or by launching more sophisticated projectiles. This means the competition between offensive weapons and defensive systems never truly ends. Every new missile technology forces defenders to adapt, and every defensive improvement changes how future attacks are planned. What we are witnessing today is part of an ongoing technological race, a race between the ability to launch weapons and the ability to stop them. And as that race continues, missile defense will remain one of the most critical components of modern military strategy. For the people living below, many of these battles happen far above the skyline. They may only see brief flashes in the night sky, but those flashes represent an enormous technological effort designed to protect entire cities. Missile defense systems continue to evolve as new threats emerge around the world. Future technologies may include laser interception systems, artificial intelligence targeting, and faster radar networks capable of detecting threats even earlier. But one reality will remain constant. As long as offensive weapons continue to evolve, defensive systems must evolve with them. The balance between attack and protection will always define the future of warfare. If you found this breakdown of modern air defense systems interesting, make sure to follow the channel, because in the next video, we will analyze another battlefield technology that is rapidly changing the way modern conflicts are fought.